I just wanted to make a quick video to go over all of the major topics that we hit when we were talking about limits and continuity. So these are going to be the key ideas that we build on going forward, talking about derivatives, and then much later in the year talking about integrals. So let's take a look at my Word document. And these are the ideas that we have hit in the last month or so. All right, so I can understand one and two-sided limits when expressed in function notation, a table, or a graph. Okay, so we've seen, we did a lot of IXLs where we were seeing and expressing one and two-sided limits when we were looking at graphs of functions. We also looked at them in table forms when we were doing the projects with Google Sheets. And in function notation, we were doing a little bit of algebraic manipulation sometimes when we were looking at functions. I can recognize and express horizontal and vertical asymptotes in terms of limits. So remember, asymptotes are lines, horizontal or vertical lines, that the function approaches when either the input or output is approaching infinity or negative infinity. And so we looked at the vertical asymptotes. We did an IXL that was really focused on that. And we also looked at horizontal asymptotes briefly when we looked at them in terms of graphs, but we spent a lot of time talking about horizontal asymptotes when we called it end behavior, and we looked at the limits as x approaches infinity and negative infinity of a whole range of polynomial and rational functions. So that's going to be important to us as well. I understand and can apply the basic properties of limits. So the basic properties of limits, I will give you a cheat sheet at some point in time in the near future when we get the definition of derivative down and start covering some examples of derivatives. But the basic properties of limits just boil down into what we were calling, mostly what we were calling Rule 1. That if you can substitute a number into an expression and get an answer out of it, that limits are well enough behaved that the limit of that function is going to equal whatever you got from evaluating that expression at the value that you were looking at. The other things we were looking at was as x was approaching 0, 1 over x was approaching infinity, and vice versa. 1 over infinity is an expression that is approaching 0. I can calculate the limit of a rational function by factoring. This is something that we're going to spend a fair amount of time doing in the next week or so. So factoring quadratic expressions and realizing that we can cancel out common terms in the numerator and denominator is something we will be doing. So we did an IXL on that. I think everybody did fairly well on that. If you're feeling a little uncomfortable about it and you get confused with what we do in the near future, then go back and work on that IXL a little bit more. I understand the notions of continuity at a point and continuous functions. All right, so a function is continuous at a point. Remember, we had that three-sided definition for it. So we need the limit to exist as we approach that point. We need the function to be defined at that point, and we need those two values to be equal to each other. Okay, so that's what it means to say that a function is continuous at 0. It means it's got a limit as x approaches 0. It means it's defined at 0, and that those two values are equal to each other. We didn't necessarily, I'm not 100% sure if we did talk about what continuous functions are in general, but a continuous function is a function that is continuous at all of its points, or at all of its points over a certain interval. We could talk about a function that's continuous over an interval. And so if we say that a function is continuous from x equals 0 to x equals 5, that just means for every number between 0 and 5, the function is continuous at that point. I can identify discontinuities of a function as removable, jump, or infinite. So remember, when we're looking at graphs, removable discontinuities is where we had an open circle kind of in the middle of an otherwise continuous function. So that was a removable discontinuity because you could just kind of fill in that circle by making a piecewise function that was defined where that open circle was. A jump discontinuity was where a function had two open circles, or an open circle and a closed circle, that were not at the same point. So the output value jumped very quickly from being, where it was coming at from the left-hand side and where it was coming from the right-hand side. And it jumped. And so that is a discontinuity that cannot be removed by defining the value at that meeting point. The other kinds of discontinuities of a function is an infinite discontinuity. So we saw that. I'm not 100% sure if we called it that, but if you think back to where we had a function where x was approaching infinity from the left-hand side and x was approaching infinity from the right-hand side, we said that the limit of that function was infinity, but that function obviously is not defined because infinity is not an acceptable output value for a function. So that's not quite a jump discontinuity, but it's also not a removable discontinuity. So we call that an infinite discontinuity if the limit from the left and right side are both equal to infinity or negative infinity. If one side is equal to infinity and the other side is equal to negative infinity, then that's a jump discontinuity. But if they're the same, then that's what's called an infinite discontinuity. I understand how to remove a removable discontinuity. That was something that we did in the IXL, where you were finding the value of k to fill a hole that would make it continuous. All right, so that is removing that removable discontinuity. You're filling in that open circle algebraically. And the thing we did in the last video was stating and applying the intermediate value theorem, which just says that if a function is continuous over an interval, if you think about the output values of the two endpoints of that interval, the function must achieve all of the values between those two output values. All right. And so we saw and went through some examples of problems where you would be applying the intermediate value theorem. So if you feel comfortable with all of these topics, then you should feel ready to jump into the next unit where we start talking about derivatives and getting into why calculus allows us to do really cool things that we couldn't do in algebra.